you, Ritesh, for agreeing to give an overview of your CMS project work today. And take it away.
Sure. Sorry for the issue earlier. All right. So I don't know why I can't see my title slide, but then the project, the research that I'm presenting today, right? It's part of a 2018 NASA CMS project. It's called the overall project is called the Aquatic Ecosystem Carbon Monitoring System, where we're trying to basically quantify like the sources, fluxes, stock of like inland carbon stocks, right? And but a part of that, like a critical part of that is making sure that we get the terrestrial fluxes, the terrestrial storage and then the fluxes correctly, especially from forest dominated systems, right? Because that's a big part of most waters. So my research today is going to focus on improving, like the research that I'm presenting today will focus on the work that we did to improve forest simulation, right? Like by forest simulation we mean the carbon stock, so biomass assimilation, biomass storage, as well as losses through like mortality, right, thinning, so all of those things, right? So that is the overall idea, like my presentation, right? And so for my outline today, I'm going to briefly talk about like our overall project again, right? And I'll also talk about why we need to improve this forest simulation. After that, I'll talk about I'll talk briefly about the module development process, how we develop this new forest like simulation module, right? And how we validated that at the field scale, and then how we did a preliminary evaluation at a regional scale, right? So before we apply it to our watershed of interest, which is the upper Mississippi River Basin, right? And then I'll briefly touch on the conclusion and then the next steps as well. So briefly, talking about our whole project again, right? So this 2018 NASA like CMS project, like our goal was to quantify carbon storage as well as fluxes in inland aquatic systems, right? So that would be rivers, lakes, ponds, right? And the reason to do that is because right now the current estimates of these fluxes, right, as well as storage, there's a very high uncertainty to it, right? Like as high as 100%, right? And you know well, like on top of that, so like the fluxes, and then the carbon fluxes that goes from the terrestrial from the terrestrial systems to the aquatic systems is also poorly constrained, like constrained, right? So like our project goal was to develop this aquatic ecosystem carbon monitoring system, and we'll showcase this system using the upper Mississippi River Basin, where we basically use a process based model. We will be using SWOT-C to basically quantify the terrestrial carbon storage, terrestrial carbon fluxes going into the aquatic component, and then also quantify all these carbon components in the aquatic systems as well, so like rivers, ponds, lakes, in the upper Mississippi River Basin. And this is the study watershed that you see on the bottom right here, right? Now, as I mentioned before, right, to simulate aquatic carbon storage and fluxes, we need to make sure the terrestrial component is constrained rigorously, right? So because especially forest, because it makes about 80% of the total above ground biomass, and it's a major component in meaty watersheds. We need to make sure that the carbon assimilation, the carbon storage, right, the carbon losses from the terrestrial systems to the aquatic systems, it needs to be constrained really well, right? And then on top of that, being able to accurately simulate this terrestrial biomass has other advantages as well, right? From from a climate change perspective, right? It's like this all these carbon projects, biomass is a big component, right? Now for our ACMS project, like our the method we wanted to develop this system was use a process-based model, right? Like we're using SWOT, the soil and water assessment tool, and then we would rigorously constrain this model, right? So through using remote sense data sets as well as in situ data sets, so that we so that the terrestrial component as well as the aquatic component of this different carbon storages and fluxes are like adequately simulated, right? And so that we can quantify these values properly. Now, although we want to use SWOT, right, and then SWOT has been widely used, in many projects, right? And so it's a major component of the US EPA Hawks project. It's used in the USTSC project. It's used in the Basins tool. Although the SWOT has been used, widely, and then there is also this, development of SWOT-C. there is a major limitation in SWOT in that it cannot simulate forest systems properly, right? And then it's critical to improve forest systems if you want to develop this aquatic ecosystem carbon monitoring system, right? To briefly talk about some of the limitations in SWOT, like with the forestry module, is that it's based on a crop growth model, right? And then the carbon assimilation, and then the allocation into different components like stems, roots, leaves. It's not like adequately represented, right? Biomass is only partitioned into above ground and like root biomass, and then there is also an issue with forest initialization. So if you wanted to evaluate certain watershed where there is already standing forest, we cannot initialize the model properly, right? With the forest biomass and then the forest age. So there was an issue, and then there are other issues with related to litter fall, dormancy for different forest systems, right? Like basically the evergreen and then the deciduous and then the mixed forest systems. So that is what we try to improve, right? In this SWOT model, and then again the goal to do that is so that we can represent this terrestrial carbon simulation from the forest ecosystems properly, right? And as I mentioned the issues before, so this is what we did. So what we did was so we removed the default SWOT forestry module, and then we incorporated a new forestry module that's based on 3PG. So I guess 3PG is a model that a lot of people have heard about, right? So what we did was we incorporated 3PG into SWOT. So SWOT simulated forest using the 3PG model. So that is how we did. And with that, what we could do is we could more accurately assimilate biomass, right? So we could partition the assimilated forest biomass into roots, stems, and leaves, so that we can assimilate losses from these different like components better, right? We also improved LAI, and with that we could all like along with the improvement in carbon fluxes, we could also improve the the hydrological and then the water quality simulation as well, right? And so we also improved the litter fall in like evergreen, deciduous, and mixed forest system, and that is critical because the carbon loss associated with foliage loss is different for an evergreen system versus a deciduous system and a mixed forest system, right? So one thing to note is that the way SWOT works, right? Like in the current version of SWOT works, and it does not allow multiple forests to grow in the same HRU. So like when we say HRU, like in SWOT, it's the basic unit where all these where all the different processes are simulated, right? So but a mixed forest system is basically like multiple forest systems in the same like in the same area, right? Because we cannot do that, so we used a hypothetical up. So like like let's say a hypothetical approach to mimic a mixed forest systems where we could spatially like match the biomass as well as the foliage losses as well like the tree losses and the LEI, but it is not simulating like a tree by tree stand, right? So it's spatially representing a mixed forest system. On top of that, we also improved like root turnover, because that's important, right? We also included tree mortality. That's something SWOT could not do before, but it's something that happens in reality, right? So tree mortality due to age as well as self thinning, so self competition. We incorporate that, and then with that we also added like outputs so that we could track all these carbon storages and then fluxes well. So that is how we develop the SWOT 3PG, right? So and if we and this paper is under review right now. It should come out like soon. But if anybody has questions related to this, we can always talk more in detail. So after
Can I?
yes. Yeah, definitely.
Are you okay to take questions
Yeah,
during?
I think it'll be much better because it's only a few minutes. So I think it'll be better that way.
Yeah. So LAI is conditioned on your foliage, assimilated foliage biomass estimate, and
Yes.
you're doing this partitioning to root, stem, and leaves. And this is interesting to me. I'm more interested in predicting these different partition carbon pools on site, as they develop to produce the forest floor material, for example,
Sure.
the litter deposition. So anyway, how do you get your foliage biomass estimate, or maybe some of these other components that?
So sure, so like all this estimations is based on 3PG, right? So the 3PG module, the way it does is it assimilates biomass, and then it based on its age, like growth conditions, it different like, and it uses this I forgot the exact term, but it uses these relationships, and and these relationships have been defined for different tree species, right? So it uses these relationships, like to differentiate, like to basically the partition the assimilated biomass into foliage and then stems and then leaves, right? So that is the approach that we take as well. So for each day of the simulation, so we calculate how much now biomass is like assimilated, so NPPC, right? And then based on that, after the assimilation is calculated, based on tree age, based on like weather, like environmental conditions, then we partition into root and then stems and then leaves. So that is how we're doing it.
Okay, so
At
it's
this
from
point.
3PG, but at the root of it, there's some kind of allometric that's
Yeah,
used.
exactly. The allometric relationships. Yes, that is what we're doing. And the advantage of using SWOT 3PG is that, because it is basically incorporating this, 3PG module as it is, and then there's a lot of research that has been done with 3PG for different forest types, right? Different, so, all these, existing, calibrated parameters can be directly incorporated. So if we had a watershed where, where we have different forest types, but, these forest types have been, like constrained using 3PG, we can incorporate these parameters. It would still need to be calibrated better, like more, but that can be a good starting point. Does that make sense?
Yeah.
Okay.
Yeah, thanks.
Sure. All right. So after developing the module, right, the first thing is we wanted to make sure that this we need to validate this new module at the field scale, right? So what we did was we identified 3 sites. So let me remove this right here. So for evergreen forest, we had this long term like forest sites available where they had measured annual like foliage biomass, total biomass, stem biomass, all these different components, right? This evergreen, Florida 1, Florida 2, evergreen Georgia. So we had these 3 sites with long-term, measurements. So what we did was, we calibrated our, module at one of the sites, and then we validated at the other 2 sites. For mixed forest systems and then for deciduous forest systems, we did not have these data sets available no matter how much we looked, right? So what we did was, so we identified sites like that were dominated by like deciduous forest and then mixed forest systems. So we identify a site in Wisconsin that was dominated by deciduous, and then a site in Virginia that was dominated by mixed forest systems, right? And then because we do not have these in situ or like field measure data sets, we constrained these models using remote sense data sets. So we used MODIS NPPC, MODIS LAI, MODIS ET, and then we constrained this model for forest simulation, right? But after that, and again, like for the simulation period, because we had only one site, we divided the, the model, like, the time period into calibration and validation. And after, constraining the model, we still, simulated, like the different biomass components, for deciduous and then mixed forest systems to make sure it made sense, right? So that is, the general approach. And after that, because, we want this model, to be useful, even for evaluating different forest management practices, right? And so we did some sensitivity analysis to see like how this forest would respond to changes in precipitation levels, changes in nitrate levels, different forest initializations to make sure that this model can be used for management as well later if we wanted to, right? So now we'll just quickly look into the results, right? So this is at the calibration site, so evergreen Florida site. So after calibration, what we see here, the blue is the simulated component, and then the green is the observed component, right? So we see total biomass, stem biomass, foliage biomass, coarse root biomass, LAI, and then foliage loss, right? And then these are annual values. So what we can see is that the new module, it does a good enough job of representing, like basically simulating these different components, right? And so we see like for example, for biomass, like in reality, what we see is that there is this big increase in air like LAI, or foliage biomass in the initial years, and after that it's stabilized, right? And then we can capture that relatively well. We captured the foliage loss well as well, right? And then we also captured the assimilation in biomass over time, right? So the forest, it captures like, I mean, it assimilates a lot of like biomass up top, but after certain years, it kind of stabilizes. So we were able to you know capture that trend as well, right? So this is the calibration side. So after calibration, what we did was we just used the calibrated forest parameters. So the only parameters that we used was these forest parameters, and then we applied this parameters at the validation sites at the other 2 sites, with and then just evaluated how the model performed, right? And this is looking at one of the validation sites. So we can see that without any further like calibration, right? Just using the forest parameters that were calibrated at a site that's different environmentally, the model was still able to like but at least temporarily like capture the trends, right? And then even the magnitude in some aspects, right? Of the different components again, right? The biomass, foliage, biomass, LAI, coarser biomass, and then all those components. We also validated at another site, right? And then we, the model again, although it did not match perfectly, but it in general was able to replicate the observed values at different sites, right? Although they were like different soil, climate, precipitation, and all of those things, right? By just incorporating the forest parameters. After that, we moved into the deciduous forest systems, right? And as I mentioned, because we did not have these in situ measurements available, we calibrated and validated against NPPC, right? LAI, ET, and then NPPC, and then we can see that and then of course the black line divides the calibration and then the validation period, right? And these are the statistical parameters. But in general, the model was able to this new forestry module was able to simulate carbon assimilation, NPPC, ET, and then LAI really well for a deciduous forest system, right? And after calibration, we wanted to see how these calibrated parameters would lead to forest biomass simulation for a deciduous system, right? So what we did was we did a scenario run where we said, okay, these are the calibrated parameters, but then we are planting the forest, and then let's see how the forest simulates, right? So the top graph shows the total biomass assimilation, stem, root, and then leaves, right? And then the bottom one shows LAI, and then we can see that the model even after being constrained with only remote sense parameters, like it can simulate the different forest components pretty well, right? We did a similar exercise for mixed forest systems, right? And so the mixed forest system, like so this is the LAI, this is ET, this is NPPC, right? So the model did okay, right? And then similarly to deciduous forest systems, we again using the calibrated parameters, right? What we did was we did a scenario again from planting, right? And then we wanted to see how the different forest components were simulated, and it simulated well, right? And this also showed that although we are using a hypothetical approach to simulate mixed forest systems where we are only simulating one plant type, instead of multiple plant types, but then we can still capture the spatial trend of LAI and then biomass, ET, for a mixed forest site as well, right? After that, as I mentioned, we did some sensitivity analysis, right? And so like we use the calibrated model, like for the evergreen forest, Florida one site as the baseline, and then we increased precipitation by certain percent, we decreased precipitation by certain percent, and then we saw the expected change, in biomass with change in precipitation, right? We also did a scenario with nitrate where we increased, where we applied nitrogen fertilizer, and then we also uh, doubled the atmospheric deposit, right? Just for a scenario, and then we could see again, the expected changes, right? We also did, a different forest initialization, right? Like one of the issue with SWAT is, like we cannot initialize an already existing forest, right? So what we did is, we did a hypothetical run, right? And so instead of planting, what if the forest was already growing, like, with like initial biomass of 150 tons per hectare, and then, like I think we used like 10 years as the initial age. With that, we saw that the biomass stabilized earlier, right? Instead of like how like how we would how it did with planting. So this also showed that even if we use an already growing forest as initial condition, we should be able to simulate long term biomass well, right? And then we also did some scenario with mortality activation, what like to see what if we turned off, so like in our model, we have the capacity to turn mortality off, like, due to cell thinning as well as age, right? And then we saw that, if we did not have that constraint, the biomass kind of grows linearly, not as expected, right? So, these mortality components that we have incorporated is critical. So after that, so now quick thing, right? So although generally seeing like we could see an improvement in forest simulation with this new 3PG module, there is still some issues that we need to like limitations, right? The first thing is we do not have disturbances, right? So the SWAT 3PG, although we plan to incorporate that in the future, SWAT 3PG right now does not have disturbances. So so the forest is continuously growing. So if there is disturbances, we need to make sure like we need to do some additional model input change, like to make sure that's captured. Like SWAT 3PG cannot simulate that right now, right? Apart from that, uh, as I mentioned, mixed forest systems, because of the limitation, how SWAT simulates forest, like we can replicate the spatial trend in like, biomass assimilation losses, LA and all that, but still like, it's a hypothetical scenario, right? And then the other, important part is that, so if you want to start with an existing forest, it is very critical to initialize the initial forest age and the biomass properly, and that is because, depending on, forest age, biomass, and what species it is, the assimilation curve could be different, right? All the, like, if it's like 5 years versus 25 or 30 years, so that's important as well. So after that, we move into the regional scale. Any questions, quick questions before we move to the regional scale? Or
So you parameterize the evergreen condition with southern pines, which I'm going to guess they're loblolly.
Yeah, those were lob.
So what's the implications of using that, but then applying? I mean, your area of interest was the upper Mississippi, where presumably the pines are not as fast growing, but maybe that doesn't matter here. Maybe it's more the proportions of foliage to stems to roots is what is sensitive here.
Sure. So before we applied in our module in the upper Mississippi River Basin, the first thing was to develop and test this module, right? So that was the important part. So because we do not have any field sites available that that we're able to provide this data, and then that is why we get into this FIA data sets. As we really tried to see if we could get some like plot scale FIA data sets, like in the upper Mississippi River Basin generally, but we could not access that. So that is why the work on the this Florida is basically to develop the module and then to test the module, that it makes sense when we move into the upper Mississippi River Basin. And you will see an application now. So so the regional scale application is on a smaller watershed in the St. Croix watershed in upper Mississippi River Basin. So this calibration will have to be done again. Now if we had in situ measurements biomass, all those things, we could really constrain the model better. But because we do not have that, we constrain the model using remote sense data sets, but then we are comparing against all these other available CMS biomass data sets, right, to make sure it is at least following the trend. And that is what we will show here. So the first part was
your intention was to use FIA data, but then you couldn't get access to it.
Yeah, we because we wanted to test this on different forests, in a speed, because our goal was upper Mississippi River Basin. If we could get it, we could definitely test it there. But we did not have that. The only data set we could get access to was this pine data, from Florida.
But I mean, how critical are the locations? Because it's just the locations that are protected. You should still be able to get to the FIA data.
Well, we tried, and maybe I don't know if we did it. We were able to get some annual estimates of FIA county average data sets, and then I'll show you the results later for that. But then that gives us only the biomass, right? But we to constrain the model, we need age, biomass, and then all these other components. If you can get get a hand of foliage, biomass, LAI, all of this but we could not get access to it.
You can get that data. That's publicly available even to the plot level. You just can't get the locations of the plots.
Yeah, I mean, maybe that's something that I spent a lot of time trying to figure out. And then I even contacted, the FIA people. I went through the US Forest Service website, and then there are these regional people that have been designated, right? And then I contacted them, and then I tell them, I do not need the location, but can we get plot scale data? But he said, county level is the lowest you can get to, if I remember correctly. And then he taught me how to get the county level estimates using those elevator or something. There's this online tool that's available. So I was able, but I could not get plot scale. And if we can get that, so we haven't, we are just in the process of developing our module, for the upper Mississippi River Basin. So we do not need to know the location. If we can get, these data sets for the tree species that are there, we can really constrain the model, right? Our forest, for the tree species that are growing there. And then, I think we could do a better job of simulating. So that would be really great, but we could not get hand that's something that we really tried, contacted people, but we could not do it.
Yeah, maybe it's how you ask the question. Maybe they interpret the question as wanting specific locations, but it seems like you don't actually need the locations. You just need the forest types.
Yep. Yeah. That, and if we can get the data sets, then it'd be perfect. Yeah, it really doesn't. Yeah.
Because what is your spatial domain? I mean, CMS projects are kind of product oriented. So you're trying to develop a national scale product, or just for the upper Mississippi?
So
basin?
I think Dr. Chi can help me out on this. At this point, I think we are trying to showcase this using the upper Mississippi River Basin. So I think, for this project, I think, we the spatial domain is at a HUC 12 level, so at a HUC 12 level, if we can estimate biomass, all this, terrestrial like carbon fluxes, right? Lateral, percolated, surface runoff. So I think that is what we're trying to attain, at this point, right, Dr. Chi?
Yes, yes. We are, this is phase one, and we just want to use Upper Mississippi River Basin as a showcase. And, we're developing all those tools, all those models. Then maybe in the next phase two, we can apply, this model or framework to the larger scale, to the like the Mississippi River Basin, per se, or the national. But it's harder to do a national. But our model is a watershed model, so we need to select a watershed. And so the Mississippi River Basin would be another target for us. But this is the first step, to achieve the larger goal.
Yeah, I should just also inform you. So there's a tree map product that was developed at the Missoula Fire Lab. It's a national map of imputed FIA plot IDs. So it's linked to land fire data sets. But that could be helpful to you, where you could, where you know that it's, say, coniferous cover in the upper Mississippi Basin. You could look at the FIA plot IDs for that place and then pull them from the FIA, the publicly available FIA database for those particular plots that were imputed to that location.
Sure. I mean, I think it'd be great if you could schedule a follow-up with you, right? It's like to how to access this like a file, because that's something that we tried, and then we tried to contact a few different people, but maybe we didn't phrase it correctly.
Okay,
but,
yeah, this isn't an FIA product. It was developed at the Missoula Fire Lab. So, and land fire also is not an FIA product. So you could you might take a look at that. I could post the link to for you in there.
Sure.
Chat. Okay.
Sure, that'd be good. And then as you mentioned earlier, getting access to those FIA plot data sets, like not knowing where the exact locations are, that would be critical as well. If we can do that. Okay.
Okay.
All right.
Go ahead.
I'll just yeah. So after that, so like when we develop the module, like the module at the field scale, so that the next thing is basically like evaluate this at a spatial, like at a watershed level, right? And then basically we use a small watershed, to test this new module, and then see if we could like estimate all these things that we want to, right? Like lateral fluxes of carbon, like carbon storage, like and all of those things, right? So what we did was we developed, like a SWOT model, like for a small watershed, like the Central watershed in the upper Mississippi River Basin, right? So that's the watershed right here. And then we, evaluated this model, right? In this model, the dark green represents, the deciduous forest. Aspen is the, the dominant forest type here. And then the light green represents the evergreen forests, and yellow represents the cropland, right? So, we developed a module. I mean, we basically use an existing model, but we incorporated SWOT 3BG into it, right? And then we tested the model, right? Again, as I mentioned before, when we go to a spatial domain, because we don't have these in situ, like data available, what we did was, we used this remote sense data sets. So we basically constrained our model for NPPC, LAI, right? ET, and then after that, we compared against these existing biomass data sets, right? And then I'll show you the results later. And I know. And that is for the carbon component. After that, we also wanted to see like the improvements in the water, like the hydrological simulation, and then the water quality simulation, right? So we also did some evaluations on that, right? So to quickly talk about the data set. So after so we developed this model from 2000 to 2020, right? And then we compared our annual biomass data sets against 4 data sets that were available, right? And so we used the 2003 the Forest Services data set, the 2005 CMS data set, the 2010 data set, and then the JRI 2020 data set. And so that is what we compared against. For the water, for the hydrological part, we evaluated at this 5 USGS stations, and then for the water quality part, we used 1 station right here, and then we did the evaluation, right? So as I'd mentioned, so initializing forest is very critical, right? For the SWOT 3PG to work properly. So we found two data sets. So we found this. The first set of data sets that we found was this one, right? This NACP above ground biomass data set, for 2000, and because our model started in 2000, year 2000, so we used as the initial, forest biomass data set, and then for the forest age, earlier we only found the forest age data set for 2006, right? So we backtracked 6 years. But later, we found the CMS 2010 data set. That also provided baseline conditions for 2000 for the year 2000. And we compared, and they were very similar. So we resorted to using this, right, for the initial forest age and then the biomass components. And then like this shows the forest age at 2000, and then this was the initial. This was the initial forest biomass, and this shows the initial forest age. After that, we calibrated the model, as I mentioned. So we calibrated the model against NPPC, like LAI, all of those things, and then we evaluated the model, right? So this shows the basin average so of NPPC, right? For forest dominated sub basin. So like for annual levels from 2000 to 2020. So the red is the observed NPPC from MODIS, and then the green is the simulated NPPC. So the model does a good enough job, right? Even at a watershed scale of basically estimating the NPPC, right? After that, and this is again a different way of looking at the NPPC. So the NPPC, like because it's a watershed model, SWOT is a watershed model. We divide the watershed into these sub basins, right? And then for each sub basins, we also acquired the MODIS data set, and then this shows the range of R square, NAC, and percent bias for all of the sub basins for NPPC simulation, right? So the R square is like about 6.5, NAC is close to 0.7. And then P bias is close to 0. It's slightly higher than 0, right? So this shows that the model does a good job of simulating NPPC like at a basin watershed scale as well as spatially, right? After that, we compared our biomass data sets against existing data sets. So the blue, so the orange one is our simulated data sets, and then the blue are the estimated data, the data products basically, right? And then the range basically shows the standard deviation. So basin average 2003 US first service versus basin average our model simulated 2003, 2005, 2010, and 2020. Now from 2003 to 2010 it's very comparable. Now as like for 2020, like if we look at the observed data sets, so the JEDI estimated biomass for St. Croix for 2002 is much smaller than what Williams et al. Similarly estimated for 2020, right? And then I was at a the carbon from space workshop, and then like it even showed that like the comparison between ESA biomass and then JEDI biomass was different. That JEDI biomass was kind of underestimated, right? And of course we do not know, but the model does a good job of simulating for the first like 3 data sets, but then in 2000 when we compare against JEDI, it's under simulated. Now there could be a multitude of factors, right? Uncertainty in JEDI, our model does not incorporate disturbances, right? And so there is issue like so if there were disturbances from 2000 to 2020 that led to this this decrease in biomass, our model could not incorporate that. So there are still some uncertainties associated with this, but generally the model like it's within ballpark of these different estimated data sets, right? So we also did a scatter plot for the 4 different data sets, and then so this is 2003, this is 2005, this is 2010, and this is 2020, and then we can generally see that so the R square is not good, right? But then the magnitude of the biomass is pretty good from 2000 to 2010, but from 2020 like the model overestimates the biomass, right? We also acquired these FIA data sets, this county level FIA data sets from 2015 to 2020, right? And then we compared against that, so this shows the scatter plot. Again, the R square is really bad, but and again, like just to point out, right? So our model was constrained only using remote sense data sets. So if we had this field scale data sets, available, I think we could constrain our models better. So the magnitude is okay, but there is like the R square is really bad, right? But generally like at least the magnitude is okay. I guess that is what I'm getting from this. After that, so we did some like hydrological simulations. So I'll quickly go over this. So we measure the model simulated hydrology well. We compared against the default SWOT, and then we saw some improvement, especially on low flows with with SWOT 3PG. We did water quality, like sediments, phosphorus, nitrogen. The model does a good job. And then we are in the process of calibrating, DIC, DOC monthly lows, right? So we had these data sets available from 2000 to 2040 initial calibration, and then the model is doing okay. Like we need to improve this further, but they are within the same magnitude, right? So with these calibrations, we kind of did some preliminary evaluations of these carbon estimates that we wanted to look into, right? So what like the watershed level carbon evaluation. So this is this plot right here shows the SWOT 3PG estimated forest biomass, right? Is for the 2005, 2010, 2015, 2020, and this shows like basically for each subbasin, and this shows the standard deviation for each of its subbasins, right? This shows the POC load, right, in sediments, and then we can see like if you look at the map right here, POC like is higher in crop dominated regions, and then it's lower in forest dominated regions. The black lines indicate the subbasins where forest is about in more than 70%, right? So then we looked into DIC and DOC in like surface runoff, right? And then as expected, so DIC, DOC is low in forest dominated subbasins, and it's higher in ag dominated subbasins, right? Which similarly, we looked into lateral runoff, and then like DIC, DOC in percolation, right? So after that, we like did some preliminary evaluations on how our SWOT 3PG compared against default SWOT for these hydrological combinations. So how did groundwater recharge change, soil moisture change, surface runoff change, and then the model showed improvement in those aspects as well. Not just carbon, but then the model showed improvement in simulating these different hydrological variables. We also did some evaluations for water quality like nitrates, sediments, phosphorus. Again, similar results, right? So in general, with the research so far, what we've seen is that we can use SWOT 3PG, right, to estimate like to simulate forest biomass basically over long term. We could constrain it better if we have observed data sets, but SWOT 3PG, it can basically help us like improve our estimation of carbon stocks over a temporal period, right? And and because we can really improve these forest like carbon simulation in forest dominated watersheds, we can also improve the fluxes from this terrestrial into inland waters, which is going to be critical for this aquatic monitoring of the carbon monitoring system. So next steps, we are going to do this work in the upper Mississippi River Basin. So we are currently working in the upper Mississippi River Basin, so basically for this whole project there. So that is a quick overview of the work that you're doing right now.
Okay, I'm confused by it. So a few slides ago, you showed your maps, and you showed the difference between simulated outputs.
For the biomass?
Yeah, let's look at biomass.
Sure.
So, okay, so those scatter plots are so flat. It's like there's no sensitivity at all in the simulations to, let's say, what's out there at the sub-watershed scale. But then the maps, you show variability in the simulations. Maybe it's a couple slides forward now.
This one right here.
Yeah. Okay.
Right.
Yeah. The previous one. Okay. So
because this is the simulated biomass for 2005, 10, 15, and 20.
And so this is a range of values here in your simulated biomass. So why in the scatter plots is it so flat?
Well, so for the scatter plot, so this is 2020. So let's focus in 2020, right? So if we look into each year, like so say for 2020, like our SWOT 3PG estimated biomass. Like if you look at the scale, it's mostly 131 to 166, right? Except for like there's a high standard deviation, and that plot shows the mean biomass for each subbasin. So I'm just using the mean values for each subbasin. So we can see like if we look at the standard deviation, there's a bigger range of like simulated biomass within each subbasin. But because I'm using the mean, like I'm plotting the mean, the mean is kind of similar across the watershed, right? And I think that is why we see this linear. So it changes year to year, but for each year the spatial variability, especially because I'm plotting the mean for each subbasin, it's kind of
okay. And so then back at the scatter plot, do the points in the scatter plot each correspond to one of those pucks? One of those?
Yes. One of the subbase, yes, that is what it corresponds to. Yes. So each plot, each dot there represents a comparison between like the simulated value versus the observed value for each of the subbasins.
Well, it still seems like it shouldn't be so flat in the scatter plot. I mean, you have a range here in the maps.
Yeah, but as I told you, like if so the top shows the mean and then the bottom shows the but you're right, but if we look at the and so we haven't looked into this data. So there is some variable, like for the simulated part, so there is some variability, right? It goes from 90 to 150 or whatever, right? So 150, like so if we compare JEDI 2020, and that is the variability we see in the simulated biomass. The observed is much drastic, and of course, I think so if you look at the observed JEDI biomass, it goes from as low as 25-30 tons per hectare to as high as 150-80 tons per hectare. So disturbances, right? It's something that we have not incorporated at all into the model. So once we start our forest simulation in 2000, the forest is continuously growing no matter what happens realistically. So that's a big limitation. It does simulate biomass like fairly well over time, but like if there were any changes to these components, that is not uh basically covered in the model, and maybe that's the reason why, but I'm not sure. That's a question. And the other thing to note also is that so because we do not know all these different forest species, right? So our model is basically simulating only two forest species. So deciduous, like aspen, and then like one other evergreen forest, I forgot the name, because because our model is constrained against this remote sense data set, right? Like so what we did was we only used two forest species, like and then we calibrated. So maybe, and that is the reason why as well, I guess, because once in SWOT 3PG, once the model reaches maturity, it does not change, like gain much biomass. So the forests that were not mature, they reach maturity and then they stay around that biomass, and then the ones that are already mature, because there's no disturbance, they stay around that. So after some time, they kind of pull towards the same value.
Yeah, I wonder if in all these sub-watersheds you have like a mix of coniferous, deciduous, mixed agriculture, and you're at that scale you're getting a lot of averaging out of those different conditions. I wonder, is there a way to kind of summarize this by forest type that might be more sensitive to, maybe it's more sensitive to at the forest type categorization than at the spatial sub-watershed scale? I'm just concerned about these flat responses. That's
sure. And and we haven't shown these results to like forests per se, and then we are hydrological models trying to get this forest simulation, right? So these are like really important feedbacks, and that's something that we have not done, right? So if I recall correctly, like so what we have tried is like we've made sure like if the estimated biomass is only forest, like say I think JEDI is only forest, right? And so what we did is we extracted just the forest outputs from the simulated from the simulated from our model, but we did not constrain them by different species, but although there are only two species, right? There's an evergreen and then a deciduous forest, like we're only simulating two forest types, and that could be a limitation as well, because we're not capturing the different forest types that are in there, which could have different biomass, and the others disturbance. I don't know how important that is, but I think that could make factor as well.
I wonder what it is about Forest Service 2003 AGB that does show like more sensitivity at least.
Sure. I mean, and I think this goes to, again, so we initialized the forest in 2000, right? And so like, we based on those, those data sets that we, that we got, we initialize the forest age and then we initialize the forest biomass, right? And, at the initial age, there are different, the forests have different age, right? So, the biomass assimilation for the first couple of years is different. But because again, I'm, simulating only two species, like there's only aspen and then there is one evergreen species, the maximum biomass that it can assimilate, like it kind of stagnates after reaching maturity, right? And then I think when we go to 2020, all the forests that are mature, they're already mature. All the forests that were not mature, they are attaining maturity. So the biomass would be kind of similar across space, right? Because all it's all deciduous and then it's all mature. So because we're only simulating two forests.
Okay. Yeah, so it's the temporal aspect here where it's the simulations are getting increasingly decoupled from the remote sensing indicators. 2003 to 2005 to 2010 to 2020, it's getting farther from being a good relationship.
Yeah. So yeah, I mean, so when we constrain our model against the remote sensors, and that is a limitation as well, because we are using NPPC, which is basically a base average value over each basin. So when we compare NPPC, the model is doing okay, right? But when we look at biomass, that's not directly calibrated, but it's a derived value from this NPPC calibration. That is where we see the issue. But yeah, I mean, that's something that we had not thought about. But you're right. Maybe incorporating further, multiple more tree species types, right? Rather than having only two. Maybe that'll increase the spatial variability, the temporal variability. I think that is one we could that is something that can definitely help. Again, and for that, if we had this FI data, we can constrain our forest, in different forest types. So that I think will be beneficial as well. But and the other thing is, again, one of the major is disturbances, right? And then and
Yeah,
then
so maybe
we
you're
have
not
not
counting for
incorporated
disturbance, and then maybe
There's
it
no
gets back
disturbance.
to if you're basing the simulated growth on southern pines, it might be quite a bit higher growth rate that you're simulating than you would observe in the upper Mississippi Basin.
Yeah, I mean, we are, trying to constrain growth, to what is observed, in the upper Mississippi River. But, the only thing that we can constrain against is NPPC, this remote sensed NPPC, because that is the only value we have, from satellite, right? We do not have, field scale, different data sets that we can use, because, we do not have forest specific data sets that we could use, right? And I think that is, where this issue is comes from. One thing to note though is that I guess but
Okay.
that's an issue that we are not thought about, and I guess it's important to make sure we look into more.
Well, we need to wrap up. I'll
Sure.
stop recording.